Good morning, everybody. This is Apex Unit 3 and the section about writing and naming compounds. So we're going to talk about how you write and name the formulas for different types of compounds. So ionic and covalent, those are primarily the bonding type that you're going to find. So what are these guys doing here? They were in the last video. They just want to be on my video again. So let's get those guys out of here. Sorry, maybe later on at some other point in time I'll bring you guys back in. All right, so let's talk about writing and naming compounds. Let's talk about specifically ionic. And we're going to go ahead and talk about covalent. And so we're going to both do the writing and the naming. So whenever I teach this, what I usually like to do is to start with the more challenging one, which is going to end up being like the ionic compounds. So let's maybe throw a couple examples up here where we're going to go ahead and take the name and we're going to go ahead and write the formula from it. So we'll start with an easy one, sodium chloride. And let's see, maybe calcium iodide. And let's see, maybe iron. Here's a good one. Iron, Roman numeral 3, and phosphate. We should probably actually do one more so I can show you another thing that ionic compounds will have a tendency to do. Let's do magnesium sulfate. Yeah, that's a good one to do. Okay, so we'll do those. And then for covalence, let's do carbon dioxide, carbon monoxide. Those are some common compounds you can probably already know about. And let's see, dinitrogen, tetra, let's say hydride. Doesn't exist, but you know, what the heck. We'll go ahead and write the formulas for those, all right? And then when we're done, we'll switch gears and we'll go ahead and we'll write the names for them, okay? So let's go ahead and start with this guy. So first of all, how do I know these are all ionic? If you look at them all, they all start with metals. All of these guys are metals. Versus over here, these guys are starting with a non-metal. So that is usually the dead giveaway that you end up having something that is ionic versus covalent. So look at that first element. You can't always go by that. And I'm going to go ahead and put a copy of this so you can download it so you have it. Also the electronegativity sheet and the periodic table. I realize you guys probably might want to have one of these handy so you can do it. So notice that these are the charges that elements have. You know, on a previous video, we already worked through those. We talked about how, you know, this is group 1, group 2, group 3, or no, this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 13, 14, 15, 16, 17, 18. Those are group numbers. And we said that anything in this group is going to have a 0 charge. This one's going to be a -1, -2, -3, -4, but it can also have a +4, +3, +2, and a +1. And so when you guys were doing all of the other stuff for the extra credit, we talked about that already, okay? How you figure out what these oxidation numbers, and that's referred to as an oxidation number, which is really the same thing as a charge, how you figure it out for the compounds, depending on what family it is. And basically, it's how far away it is from the nearest noble gas. Anything in this family here is 0. But if you look, this guy only needs 1 more electron to be stable. When it gets it, it'll be a -1. This guy only needs 2 more electrons to look like a noble gas. So when it gains it, it'll have a -2 charge. What do these guys do? They lose electrons. So if you look at beryllium, you know, it has 4 electrons around it. It wants to try and look like helium, which is 2. Well, how's it going to do that? It's going to lose 2 electrons. So it becomes +2. And the reason why that it loses is because of electronegativity. These guys have low electronegativity, so they get rid of them. These guys have high electronegativity, so they take them. All right. Okay, so properties that we've already talked about so far in some of the videos. So let's go back to this. We're going to just use this sheet, okay, our ion sheet, to figure out what it is. So notice that there's some words up here: cations, anions, and polyatomic ions. Cations are anything in the first column. Anions are anything in the second column. And polyatomic ions are anything in the third column. Pretty easy, right? Well, what do you notice that there's a pattern about? That these guys typically have a positive charge. That's why they're referred to as cations. These guys typically have a negative charge for most of them. That's why they're called anions. Polyatomic ions, poly means many. They're more than one element, but together they act as one element. That's why there's a little set of parentheses up here, because we typically wrap them in parentheses, showing that that bond is real strong and it usually doesn't break. And they act like one element, and it has a charge associated with it. Now, I want to talk about these guys. Notice that both of these guys have a +1 charge. And because they both have a +1 charge, if you have a compound starting with one of these, it's going to actually be ionic. Really both, because you've got covalent bonding going in here, but the whole entity is going to act like a metal, and it's going to basically get rid of an electron to a nonmetal that would join with it, just like other metals do. Metals typically have a positive charge or a positive oxidation number, right? And so usually it's something from the first column that you're going to start with, but every once in a while you can also start with these guys. And if you start with these, then it's going to end up being ionic as well. All right. Okay, so let's do this. So sodium, let's look up sodium on our little list here. Down here it is with a +1 charge. So we're going to write down Na, the +1 charge. And then we'll look up chloride. Now, chloride sounds like chlorine. Notice on my little chart here, I put "ide" in here. That's because a lot of these guys typically have an "ide" ending when they're in a compound. So you're going to find it there. So there it is, chlorine. Now, there's a whole bunch of charges. Well, which one is it going to be? Well, usually the first one is the most common charge, so you could just pick it. But it's reasoning. Just take a look. If the first one's positive, what's it going to stick to and bond to? Is it going to bond to another positive? No, it's going to push away from that. So it's going to have to be something else that's negative. So that would be the -1 form here that would end up being with, okay? So we'll put a Cl with a -1. And then Miss Campus Buddha likes to use the crisscross applesauce idea, and that's really what's going on here, is that this one comes over here and comes down, and then this one comes over here and comes down, and they go from being a superscript, so they're a superscript up here, to basically a subscript down here. So that would be NaCl. Now, typically we don't write the ones down here. So even though this one is now after the Na down here, and this one is now after the Cl down here, we do not write the one. It's assumed to already be there. Only if it's 2 or higher would you write it. All right, on to the next element, or next compound. Now, we can't call these guys molecules because they're ionic bonded together. They're not covalently bonded. We could call these guys molecules if we wanted. All right, so calcium iodide. If we look up calcium, it's a +2. So Ca +2. And we look up iodine. Notice the iodine's got a whole bunch of charges. What's going on there? Well, remember, same idea up here. If this first one's positive, grab that -1 for the iodine, and there's only one of them that it could be. It's the -1. And so when you crisscross applesauce that guy, you get CaI2. Why does it happen? The one comes down here from the superscript down to the subscript, and then this charge, or this oxidation number, comes down here and turns into a subscript, and it is a 2. And so that's how you would go ahead and write the formula for that. Okay, these are pretty easy. Let's get to some ones that are a little bit more complicated. We look up iron here, and iron is Fe. Now notice there's 2 charges, 2 oxidation numbers. So which one are you going to use? Well, that's why they give you the Roman numeral. It is the actual charge. You're going to use a +3. So you don't even need to look at this chart to figure it out. Whatever the Roman numeral is, doesn't mean the third one in the group. It just means that's its actual charge. That is a +3. Now, what about phosphate? That doesn't sound like an element. That sounds like something different. So it's probably over in the polyatomic ion section. And there it is. It's PO4 with a -3. But notice at the top of the sheet, I wrote a set of parentheses. We're going to include that when we go to write this down. I'll show you how to do that. This will be PO4. You wrap it in parentheses, and then you put the -3 on the outside like that. Okay, now let's go ahead and swap these guys. All right, so if we swap them, this 3 comes down here. This 3 comes down here, and you end up with Fe3PO4 3. Now something interesting happens, kind of like algebra here. Both of these numbers are divisible by another number. They're both divisible by 3. So you know how you can reduce fractions if you have something that's 3/3. That's like saying 1/1. Or if you had something like 6/3, you could reduce that to 2/1. You can reduce these guys too. Both of these guys, the 3/3 were reduced to 1 and 1. So that gives you FePO4 like that. Now, another thing happens here. See these parentheses? You can remove them. Now, the reason why you need the parentheses is so when you have a number out here, it means to triple what is in here. Otherwise, if you left that parentheses there, it would look like the number 43, right? So you have to be careful of that. So the 3's reduced to 1 and 1, and because there's no number out here now, we can just write FePO4. That is the final answer for this problem. Okay, so that brings up another idea here. How do you figure out the type, how many elements you have for each compound? I mean, for each element in this compound. You got 3 irons. You've got, now this 3 means triple this PO4 group. So 3 times the 1, you got 3 P's. And you do not have 4 O's anymore. You have how many? That's right, 12. 3 times 4 gives you 12. So that's the atom inventory for that compound. There's 3 irons, there's 3 P's, there's 12 O's in there. All right. Okay, so let's move on to the next one, magnesium sulfate. So we look at magnesium, it's a +2. We look up sulfate. Sulfate is SO4 with a -2. It's one of these dudes from the last column, so it's going to get parentheses. So we're going to write down SO4 with -2. Like that, and let's go ahead and crisscross applesauce this dude. And we get MgSO4 and a 2 and a 2, but remember, if you have something like 2/2, that reduces to a fraction of 1 to 1. So both of these guys are really turning into 1s. It's just MgSO4. Because we know how to do 1 out here, we can drop that parentheses. All right. You don't always drop the parentheses, only if you have a 1 on the outside here. And since these 2's reduce down into 1 and 1, we can remove it. You know, if this was, like, say, Mg, and there's, like, no number here, meaning it's a 1, and it's SO4 and a 2, you'd have to keep the parentheses around the SO4, because you couldn't reduce these 2 numbers, all right? But in this case, you do. So that's how you write the formulas for ionic compounds. Let's now take a look at covalence, all right? And actually, before we do that, we should probably maybe go the other way around. I'm thinking maybe it might be better to, since we wrote the formulas, you know, this is basically how we write the formulas for these guys. Formula and formula. Let's stick with the same type of element. Let's stick with ionic. But we're going to work with naming them. And then over here, we'll do covalent, where we just simply name them. I think that's a better way to do it. Just that way we can stick with the same ion sheet here that we have, since we're on that same trend. So let's throw a couple down here that we might have. Let's say that we're going to do magnesium this way. Went this way. MgOH2. Let's say we're going to do that compound. And let's say that maybe we're going to do another one like Fe. Fe, and we'll do SO4. And then this will end up being a 3, and this will end up being a 2. And I probably should do another one because there's some interesting things that can happen when you're going the other way around like that. Let's maybe do PB and CR2O7. We'll do those guys. All right, so let's go ahead and do the first one. MgOH2. So you just simply look on your sheet. You see magnesium. It's a +2 charge. Now, notice something. There is only one charge for magnesium. And there's a reason why I'm saying that. So I'm going to just write down magnesium. And the reason why I'm saying that is because, remember, sometimes you have elements that have more than one charge. And when they have more than one charge, like this guy right here, down here, you have to use a Roman numeral to say which one it is. Okay. Well, we're lucky. Magnesium only has one choice, so we just call it magnesium. And then OH is something over here. There it is. It's called hydroxide. Let's move to the next one. Fe is here. It's called iron. So we'll write iron down here. But we have to be careful. There's more than one choice here. There's a 2 and a 3. And we have to figure out which one it is. Okay, so how do you do that? Well, reverse cross, right? This 3 came from the iron. That means this 2 came from the sulfate. So let's just double check and make sure everything's okay on the sheet. And if that's true, sulfate should have a -2 on here. And if we look, it does. Okay, that would mean that this one is correct as well, the +3. We chose the right one. If this one wasn't right, then that means that this one would probably be messed up as well because something got reduced. And I'll show you that on the next one, right? So because this one's correct, then that means that this one's going to end up being correct. So iron, Roman numeral 3, and then SO4 is called sulfate. So again, the reason why we have to say the Roman numeral 3 is because the iron has more than one choice. All right, we have to say which one it is. Now for this tricky dude right down here, this PbCr2O7. Okay, Pb on your sheet is a lead. It's right here. Pb, and it has 2 or a 4, so we don't know which one it is. So we know we need a Roman numeral. So lead, we'll go ahead and put the parentheses there because we either have to put a 2 or 4 in here. And then let's look up Cr2O7. That's something over here. It's dichromate. So we're almost done. So we look up the Cr2O7, and its charge is a -2. So this guy had a -2. And let's see if that works out. When we reverse cross this should be a 1. What happened there? Because it's really a 2 and this should be a 1, that means that this number got cut in half, all right? And so we have to double what's down here. This 1 that's normal here got doubled to a 2. Well, what's after the Cr2O7? Cr2O7, it's not the 7. Remember, there's really parentheses that goes around this guy right there. And so there's really, I'll make them white, there's really a set of parentheses here. There's a 1 here. Well, if we doubled this 1 to make it a 2, then we have to double this one to also make it a 2, right? Because 2 and 2 would cross out and turn into 1 in 1, right? They would reduce. So this is really Roman numeral 2 dichromate, right? It is not Roman numeral 4. If this were a 4, you'd have a 4 here and a 2 here. And this 2 and the 4 would turn into the numbers of 1 and 2. You'd see a 2 out here. We do not have that. So let's go over that again, because that was kind of a little tough one here. So we look up lead in a little sheet thingy. Lead has a 2 and a 4. Okay, which one's it going to be? We don't know. Let's look up chromate. It's dichromate. It's Cr2O7 with a -2. to CR2O7. So this 1 should be here. It's not. It really should be a -2. That meant that this number was doubled. So whatever number here is also double. Well, there's a 1 here. So if we double, we get a +2. So this was the lead-2 dichromate. Okay, doesn't happen often, but you do have to be careful of ones like this, where not only do you need a Roman numeral, but things end up being reduced for you. All right, let's go on to the covalence. So this is a sheet that we use for ionic. I have it titled as ionic. What do you use for something that is going to end up being covalent? Well, let's just go back to our old periodic table like this guy right here. I'm going to label the top covalent. And I'm going to put some prefixes down here. I'm going to put the prefixes for 1 through 10 and what they are. So 1 is mono, and 2 is di, and 3 is tri, and 4 is tetra. And many of these guys you've heard before. 5 is penta. And then we have 6, which is hexa. And then we have 7, which is hepta. And we have 8, which is octa. And we have 9, which is nona. That's a weird one. And then 10 is deca. We're going to use those prefixes to write the names and formulas for covalent compounds. All right, so let's give it a shot. So they follow a whole different set of rules. We don't have to worry about crossing charges here, okay? So we look up the word carbon, and we say, okay, what is that on the periodic table? It's right here. It is carbon. It's just a big C. And then dioxide sounds like oxygen. Remember, the ending changed to an "ide", so that's here. And the abbreviation is an O. Now we got to pay attention to the prefixes. What does di mean? Well, if you look, di meant 2. Now be careful. You might think, oh, dioxide, I got to cross that number over where the carbon is, like I did over here. No, don't do that. That dioxide means how many O's you have. So put that number right after it. So CO2. Notice the first one doesn't have a prefix, so you don't have to put anything here. It's assumed to be a 1. Let's move on to the next one. Carbon. Carbon, there it is. It's a C. Monoxide. Okay, that sounds like oxygen, but it's got the prefix mono on the front, or mon. You don't want to have two vowels next to each other, so one of the O's is dropped. So CO, like that. And what does mono mean? Mono means 1, so there's just one O after here, and you're done. So just CO, that's it, okay? Now notice something different happens here. Now we start putting prefixes on not just the back one, but the front one. So we're going to have to pay attention to that. Nitrogen is N. Right here, nitrogen is N. And then again, we've got, oh, this is a different one, hydride. Hydride sounds like hydrogen. Okay. So hydrogen. Notice that this is 2. Di stands for 2 right here. So put N2. And then the H picks up a tetra is a 4. Okay, now you might want to think, oh, I got to reduce that, right? 1 to 2? No. Do not reduce covalence. Only reduce ionic type compounds. Do not do that for covalence, okay? All right. So let's kind of summarize the only rules you got to pay attention to here. Number 1, you got the prefix on the second element corresponds with the subscript over here. And notice here something interesting happens for the first element. If the first element is really mono, we don't write monocarbon, we just assume it to be there. We don't do that for the second, but for the first element we do. Why? I don't know. Somebody came up with that idea. So monocarbon, we just don't write the mono, and then this is dinitrogen. So let's now go the other way, where we're going to go ahead and name some compounds. So let me throw a couple down there that we would do. Okay, so maybe we'll do PO5. And maybe N2 up. And, well, we'll just do those two. I think that's kind of good for now. I think you can get the idea from these two. So let's go ahead and do this. So we look up P. And we'll say, okay, what the heck is P? P is right here. It is called phosphorus. So we're going to write the word phosphorus down. There is no number here. So you might think, oh, I got to put a mono in front of that, right? Well, remember what we noticed? That if you have the first element only gets a prefix if it's basically 2 through 10. So let's say that you had two elements, all right? Let's say for a compound, it would be, this would be element X, and this would be element Y. X for the first one, Y for the second one. This guy, if it's 1 through 10, you use a prefix. For this guy, you only use a prefix if it's 2 through 10. Otherwise, there is no prefix that you use. So that's really the only rule you got to remember for this. First element, second element, 2 through 10 prefix, 1 through 10, which means always. So you always use a prefix here. Not always necessarily there. Okay, so phosphorus, we don't need a prefix because it's a 1, not a 2 through 10. O stands for the element oxygen, but remember, the second thing for covalent compounds, the other trend is they end up with an ide ending. So this is not oxygen, it's oxide, and we are going to need to put a prefix in front of there, whatever the prefix for 5 is. Well, the prefix for 5 is penta. So this would be called pentaoxide, or then there's two vowels, you just drop the lower vowel, so pentoxide would be actually its real name. So phosphorus pentoxide, and this should be one word here. I just had to squeeze it in there. Okay, how about this next one? N2O. N is nitrogen. O again is going to be a oxide ending, and I'm going to leave some space there, a little bit more space so I can put that prefix right in there. Okay, notice that this one has, the second element does have a prefix. It follows our rule up here, 2 through 10, you need a prefix. So what's a prefix for 2? Well, it's di. So we'll call this guy dinitrogen. And what about the next one? What's the next one going to be? There's a 1 here. What's a prefix for 1? Prefix for 1 is mono. So this is going to be, and again, you don't need to put 2 O's there, so just monoxide. That would be how you would write the name for that covalent compound. So there you go. You've got a lesson on how to write the formulas for ionic and covalent, and then also how to write the names for ionic and covalent compounds. So thank you very much for watching, and the next unit that we will cover will be Unit 4. Bye.